Okay, so we stopped yesterday with this long uh, summary of long and incomplete summary of the gravitational wave, possible gravitational wave production mechanisms in the early universe. And I will go on today with some general considerations on the spectra that can arise before then providing a bit more detail on some of these mechanisms. Okay, so in general, so when one wants to find the gravitational signal from a stochastic source, one needs to solve this equation that we derived in the first part of the course. And it is possible, I think, to classify the sources of so the sources of gravitational waves and therefore the processes giving rise to anisotropic stresses in broad categories. In general, so as we already said in the beginning, from the background energy momentum tensor, what doesn't have any source of gravitational waves because it is a perfect fluid. Diagonal, the energy momentum tensor is diagonal and therefore there is no transverse traces component. And indeed, any form of energy with a transverse traces component cannot be accommodated in the Friedmann space-time. But at first order in perturbation theory, of course, that's possible. Now, the thing is that in reality, most mechanisms, one will go always more or less at second order. Here, for the energy momentum tensor, as you can see, for example, one can have a transverse traces component if in the universe there are large-scale scalar field gradients. And this is the case, for example, during inflation or preheating. Rather during preheating, I would say, but also during phase transitions, if the scalar field is the one that is undergoing the phase transition and the phase transition is, for example, first order. One can also have periods in the early universe in which there is some bulk fluid motion. And in this case, there could be some transverse traces component, if in the velocity distribution of the early universe fluid. And you see this is also second order in what is in general considered a first order quantity in cosmological perturbation theory, which is the velocity, the bulk fluid velocity. One can also have the presence of electromagnetic fields, and in this case, really just, the energy momentum tensor does have a transverse traces component always on its own. And then, as I already mentioned, one can have pi ij from second order scalar perturbation, so from combinations of gradients, space gradients of the Bardeen potentials that are in general considered to be zero at first order in perturbation theory. Okay, so you see the fact that one needs to go always somehow second order, right, means that in general, if one just considers the vanilla scenario of a Friedmann universe with superimposed inflationary small perturbations of inflationary origin of the order of 10 to the minus 5 in the scalar component and not in the vector one because they decay. So this particular scenario, which is the one that we infer from the observation of the cosmic background, does not produce gravitational waves other than those that come directly out from slow roll inflation. Okay. So all these active generation processes must resort to non-standard phenomena, as we said before, and in general must resort to the presence of a very high anisotropic stress component, and which takes the form of something that we are usually used to consider that it is a second order in cosmological perturbation theory, but in this kind of sources, these particular sources become big. Okay, for in general, this occurs for a short amount of time, but we can also have sources that are extending in time that still fulfill the cosmological principle, in general. Okay, and as I already said at the beginning of the lectures, the components of the anisotropic stress must be treated as random variables because we cannot access the detailed properties of the generation processes at the moment they operated. This is in general true. So if they must be treated as random variables, it means that what we need to model is the unequal time correlator of these anisotropic stresses that source the gravitational waves, and in general the power spectral density is written in this way, where we always have this delta that comes from the homogeneity and isotropy, and the underlying assumption of homogeneity and isotropy of the source. And this is the power spectral density of the anisotropic stress taken at an equal time. And we will see why we need actually to cross-correlate at an equal time. Okay, now I would like to proceed with two approximate analytical solutions to this gravitational wave propagation equation that are only valid within some assumptions, but that are actually quite often verified. And they are of two broad categories. The first one is when the source, so the first case in which one can find a decent approximate solution that expresses some general properties of the gravitational wave signal is when one assumes that the source is fast, which means that it operates for much less than 1 Hubble time. And this in general gives rise to peaked gravitational wave power spectra. And here you have an example in this figure, which is a bit a busy figure, but we have omega gravitational waves today as a function of frequency. The colored regions here are the sensitivity of pulsar timing arrays, LISA, and third generation Earth-based detectors like the Einstein Telescope and Cosmic Explorer. And you see that typically there are these two examples of peaked signals. They come from domain walls and first order phase transitions, and the large scale part is proportional to F cube. And this is what we are going to derive now. The other category are sources, as you can imagine, since the first is fast sources, the second is continuous sources, which means sources that operate for several Hubble times. Okay, and when I say several, I mean can be also throughout the entire evolution of the universe. And in general, these kind of sources provide gravitational wave power spectra that are flat in frequency, not peaked. And typical example are cosmic strings. And there is the possibility, of course, these sources are particularly interesting because they open up the possibility of having coincident detection at several observatories, and therefore reinforce the inference of the source characteristics by the detection, the coincident detection by independent measurements. Okay, now let's go to then the fast source. Okay, so we assume it operates in a time interval eta final minus eta initial. Eta is the conformal time in the radiation dominated era, and we have already seen, provided at the beginning of the lecture, the general solution in this case is very simple to obtain. okay? Because once the source has stopped operating, we just have freely propagating waves with coefficients that are obtained by the matching at the final time of the sourced solution with the homogeneous solution, okay? And so we have already found, or I have already given these coefficients in terms, in a general form, in terms of a generic source, pi k tau, okay? And now I want to go one step further and say, okay, let's see if we can say something pretty much general about the gravitational wave power spectrum. If the only thing we assume about this source here is that it operates fast, so that eta final minus eta initial is much smaller than the Hubble scale, the Hubble time. Okay, so what we are interested in obtaining is the gravitational wave energy density power spectrum today. And today, as I already told you, we are only interested in modes that are far into the horizon, so that satisfy k eta 0 much larger than 1. Okay, and in this particular case, the gravitational wave energy density spectrum takes this form here, where we have this factor k squared times the power spectrum, or the power spectrum of the amplitude of the gravitational waves written in this way today. Okay, so this was given, I think, in the second lecture. Okay, and now we think about just substituting this particular form, this particular coefficients into here. And this will actually make appear the unequal time correlator of the anisotropic stress. Okay, so here you imagine that you will have two integrals. Okay, so each of these factors of each of these amplitudes here entails a time integral. And so it is the product of two integrals taken at different time. Okay, so we will have two integrals and pi r at tau and pi r of another time zeta. And then we have this average here that can enter the integral and operate on the source. So on the product of the source to give rise to this particular source here. And that's what enters, in the gravitational wave energy density. So we have these two time integrals. This is the green function. So we take the green function here. We will have products of sinus and cosinus that can get out, of course, of this correlator, and we can rewrite them. Sorry, they get also, of course, mixed with this kind of sinus and cosinus that are taken at k eta naught, okay, which is the freely propagating solution today. And we can rewrite all these products of sinus and cosinus just as the cosinus of the difference of the times. And here there is a mistake. I'm sorry, this should be a tau. Okay, so it's really the difference of the times over which we are integrating. Okay, so we find this particular expression for the gravitational wave energy density today. So two time integrals up to eta fin, because we have performed this matching and we have our source. Okay, up to now things are pretty much general at the level of the source, but now we suppose that indeed this interval eta final minus eta initial is much smaller than 1 Hubble time. at the moment of the source, at the moment which the sourcing process is taking place, which is this little star here. So this means that we can approximate the scale factor here as constants, okay, because we are just restricting over a smaller time interval over which the universe is not evolving. Okay, and we also have, so we focus on the solution at large scales, okay, still, of course, well into the horizon today, but scales that are larger than the inverse, than the, let's say, than the Hubble scale at the moment of generation. Okay, so eta in is basically, so H star is basically 1 over eta in because we are in the radiation era. And so we focus on this particular case, which means that we are now looking for a solution down here below the peak that corresponds more or less to the Hubble scale or smaller than the Hubble scale, as I was saying also before. Okay, and so, and then we make a further assumption that is, okay, let's suppose that pi is actually can be considered as constant over the time interval of operation of the source. Okay, so over the time interval over which we are integrating. And we will justify this assumption in a minute. For now, let's consider it. So we remove all the time dependence, and therefore this thing gets out. Okay, and so this comes then this is then the solution for the gravitational energy density parameter. So I have further divided by rho critical today. Then for modes that are inside the Hubble scale today, but outside the Hubble scale at the moment of the generation process, so large scales. Okay, and here basically I have just rewritten these integrals, but the main point appears. So here we had this k cube, okay, k cubed that comes from all these combinations of h and sorry. And pi here, you know, there is a 1 over k that becomes a 1 over k squared. I mean, if you do it, you will see that in the end, you end up with a k cube. And then I transform this p of k in some dimensionless quantity, and I account for the dimensions of the delta by putting an L cube here, which is, you know, the typical scale of the anisotropic stresses. Okay, so this is just a renormalization that get absorbed in this new definition of p twiddle. I mean, this you can also do. Now, this p twiddle is dimensionless, and of course, I've taken out also a dimension for the energy density in the anisotropic stress is squared. Okay, and then one normalizes to the radiation energy density in the universe at the moment of the generation, and then you know, if everything is done correctly, you get an extra h star factor that you can multiply or put together with this delta eta that now comes from the time integration, because the time integration, you see, is now very simple. This thing here has come out of the integral. The cosinus here, because of this particular assumption, okay, that k here is always smaller than eta in, of course, here the dominant part of the cosinus becomes just 1. And therefore, these two time integrals, they just give the time interval eta fin minus eta in, so delta eta squared. Okay, and that's what comes out here. Right, and now, so this is this final expression. I think it was also in the probably in the exercises to verify it. You need to balance all the h squared, rho rad with rho critical, etc., to get this omega rad. In the end, it turns out fine. And then let's try to see, typically what can we get to get an observable signal. So, for example, for pulsar timing arrays, what they have detected for omega is of the order of 10 to the minus 9. Okay, which means now all these are just cosmological factors. This is of the order of 10 to the minus 6. Okay, these depend very slightly on the generation epoch through the number of relativist degrees of freedom, but I mean, for an order of magnitude estimate, this is utterly negligible. Okay, and then to balance things out, one finds that this particular combination, because here I have normalized everything, okay? So if we assume that we are around the peak of the spectrum, so for k of the order of 1 over L, this particular combination must be of the order of 10 to the minus 3. If we consider LISA, okay, that is a slightly more sensitive than pulsar timing arrays today, this factor remains the same, and here we find something that is of the order of 10 to the minus 5. So what one gets out here from this order of magnitude estimate is that only slow and very anisotropic processes have the chance to generate detectable gravitational wave signals for subbubble sources. Okay, so we really need a lot of energy in anisotropic stresses with respect to the energy in the universe, available in the universe at the moment of generation. And we also really need processes that operate for an amount of time that, okay, here the basic assumption that it is shorter than the Hubble time, but the closest it gets to the Hubble time, the best it is. Okay, and now let's see the characteristic of the spectrum. So all these factors here provide the amplitude of the signal, while this particular dependence on k gives the spectral dependence on omega. Okay, and this within the assumption that we are considering a fast source, this cross correlation here, or spectral density, we expect it to be uncorrelated at scales that are larger than the typical scale of the anisotropic stresses, okay? Because the process, by causality, the process is fast, it will have, the source can have features, etc., at small scales, but at scales that are larger than 1 over L star, in general, we expect that it is fully uncorrelated, and therefore that the particular spectral density here is just white noise. Okay, so this is the typical shape of the source power spectrum or a spectral density for a process that is operating on a very defined time interval in the early universe. So it is white noise. It will have it can change at wave numbers that are of the order of the characteristic size of the anisotropic stresses, and then it will have a slope that really depends on the details of the source. Okay, and so our final result concerning the spectral shape, okay, is that at this particular wave numbers that, as I said, are much larger than the Hubble scale today, but smaller than the Hubble scale at the moment of generation processes, at the moment of the generation process, which in itself by causality must be smaller than the characteristic scale of the anisotropic stresses, okay, characteristic scale of the source, then this quantity here is simply flat in K, and we get that omega is proportional to K cube. Okay, so this is the general result that we have worked out for this first time together with Ruth Durer many years ago, is that causality causes this particular gravitational wave parameter to behave as k cubed at large scales. Okay. Now, we have actually assumed that pi is constant, right, over this time interval. I mean, is it a good assumption? The answer is actually yes. And if one examines what would be the characteristic time of the source, okay, one can say, well, I can imagine that the source is going to be correlated or characterized by a characteristic time which should be of the order of the scale of the anisotropic stress is divided by some quantity that here I represent as a sort of RMS velocity. Okay, RMS velocity. Okay, this is of course, very much is exactly this in the case when gravitational waves are produced by bulk fluid motion, but one can associate some energy here, also to other kind of processes. And now the key observation is that the characteristic time of the gravitational wave production from the Green's function, okay, the Green's function that is just here, sinus, is 1 over k. Okay. And therefore, for every sort of wave number that satisfies this inequality, you can verify that the gravitational production goes faster than the source evolution in general. Okay, so for high enough wave numbers, and of course, this depends on how small, the extent over which one can assume or one can deduce this characteristic depends on VRMS, but this is always for sure smaller than 1. Okay, and even if we consider our more general production, this is going to be corresponds to a relative energy with respect to the total energy density in the universe, and so it is in any case smaller than 1. Okay, so there is going to be a range of k, which in general includes the spectral peak, for which the gravitational production goes faster than the source evolution. And therefore, for this particular range of wave numbers, it is justified to assume a constant pi. Okay. Because of this characteristic. So one can assume that the source is constant in time. For a finite time interval, this can be larger than the Hubble time. Okay, and this will be, the typical time over which the gravitational wave are sourced. Okay, and I write here that is some number times the characteristic time of evolution of the source. Okay, they needed coincide. And within this assumption, actually, one can easily integrate here, even without all these assumptions, to find the gravitational wave spectrum. Okay, and this is the final expression. And so there is going to be this k cube. There is going to be the full, in this case, because the only restriction is this, the full spectral density of the source, and there is some modulation. Okay, and here I show what it is, the spectrum that if you look into many processes of gravitational wave generation, you will find it. Okay, it is in general this k cube at low frequency. This is just due to causality for an uncorrelated source, as I showed you. But then in general, there will be some behavior, okay, that will be linear at intermediate frequency, and this is typically goes from the inverse duration of the source to the peak. Okay, so this can be more or less, these two scales can be more or less separated, okay, depending on the features of the source. At the peak, we will have an amplitude that in general scales as the squared of the energy density that is available in the generation process and the squared of this particular ratio between the characteristic size of the anisotropic stresses and the Hubble scale. And then we will have a slope here that really depends on the generation process. Here I've taken this figure from this paper that considers turbulence, and therefore the slope is k to the minus 8 thirds, but that's not at all general what happens here. However, this large scale behavior is indeed quite general for fast stochastic sources. Now for a continuous stochastic source, let's see what happens. Here the typical example are topological defects. Oh yeah, so I failed to tell you actually the typical example are first order phase transitions in this particular case, because in this case the source of gravitational waves occurs very fast because it is linked to the bubble production. And therefore, typically it lasts less than one Hubble time or a few Hubble times if we link it to the bulk fluid motion. On the other hand, topological defects in general can source gravitational waves through the entire universe evolution once they have been produced. And the reason is, so they are typically produced after a phase transition. We will see a bit more detail in the following. They are typically produced at a phase transition, but then they form a network that is evolving with the universe evolution. And this network remains of topological defect remains there once it is formed. So how to treat these sources that are continuously operating during the radiation dominated era? Of course, one does not match with the free wave solution at the end time of the source, because there is no end time of the source. Okay, so and the source never takes really the form of freely propagated subbubble modes. Okay, so one needs to deal directly with this quantity that is the gravitational wave amplitude. Okay, multiplied by A. We have seen it in the beginning. And here there is no final time, but there is just a generic time at which you want to know your solution, okay, which will be specified to be the time today in general. Now, once again, we take the energy, gravitational wave energy density. We need to find, actually, this is in terms of little h. So from this particular solution, one needs to divide by A, and one needs to take the time derivative with respect to conformal time in general. And so this makes, this will have a term which is a little h prime, a term that comes from the derivative of the scale factor. And in the end, if everything goes out smoothly, this is the expression you find, where this is now, again, the green function. Okay, that now that doesn't take this simple form as before of cosinus of k tau minus zeta, because we have not matched with the freely propagating solution. But one still gets the 2-point correlation. The 2-point correlation function of the anisotropic stress energy of the anisotropic stresses at different times. Okay, and here we are integrating up to some indefinite time eta. Okay, because the source is continuously producing gravitational waves. Okay, and now let us put a bit more detail into this source, otherwise we cannot go further. And so in general, if we specify two topological defects, one has several properties here, and in particular, the most important one, okay, we will have clearly an energy scale. So this is a vacuum energy here connected to the phase transition. So we will have that this will contain an energy scale, obviously, but in general, in this particular case, one has that the unequal time correlator is actually very much concentrating on the diagonal, so when tau is equal to zeta, and decay is very fast in the off-diagonal component. Okay, so this is pretty much very much different than the assumption of a constant pi that we did before. And also, in general, one can expect that this quantity decays somehow at equal time, okay? And this is because each source will clearly lose energy as the universe evolves, and in particular for topological defects, it decays as a power law. Okay, so if we consider these characteristics, these features of pi, which here I precise, you know, they are given in terms or inspired by the condition, by the source being topological defects, but I must say they are quite, you know, logical features for the source of gravitational waves. There is nothing very strange into all this. And then one sees that indeed, because of this decay here of pi in general, the source becomes progressively independent on the upper bound here. Okay, so the point is that the reason why we actually get a flat spectrum at subhorizon modes, okay, here I specified this is in the radiation era. It was the basic assumption of all the two examples. Okay, the reason why we get a flat spectrum is that as time progresses with the evolution of the universe, the source decays. But the build-up of the source is an integrated process. But since the source decay, well, this integrated process actually does not change much, okay? And therefore, so this integral after some epoch does not change much, and the result is something that is actually independent on frequency. Okay, and this here you see a typical behavior during the radiation era for a network of topological defects. You observe that the spectra are absolutely flat in frequency. During the matter era, which is what happens here, things change, but they do not change because of the characteristic of the source, but they change because of the typical transfer function, so of the fact that here all these time factors here are different, of course, because the scale factor changes. Okay, so basically, yes, this was just somehow a guidance to interpret what you can find in papers, right? Because there are so many results on gravitational wave spectra from early universe sources, and you know, it's not that all of them can be read into these two broad categories, but in general, it is the case. Whenever you see a peaked spectrum, is because the source is operating localized in time. Whenever you see broad spectra, on the other hand, is because the source is operating throughout the universe. Okay, and I just wanted to give you a hint of what are the characteristics of pi, or what we can assume to actually find the behavior, these two categories of behavior, and in particular the k cubed at large scales for fast sources. I will now go on with more examples of signals, so more detail on some example of signals, but maybe I can take questions on this first part if there are.
The question.
Ma'am, just one question about the topological defects. So, like, you didn't mention the dimension of the topological defects, it's like monopole, strings, or texture. So, could you tell, like, how did it affect, like, the boundary condition or anything, or any kind of topological defects is fine, or is it like monopole?
Yeah, in this case, it doesn't really matter. Okay, which kind of topological defects we are. I mean, it's so no, it is not fully true what I say. So basically, if we have topological defects, for example, domain walls, right? Domain walls, they have the wrong behavior with respect to the universe evolution. So they tend to dominate the universe. Okay, so domain walls, you need to annihilate them. So in that case, typically because of this reason, not because of some fundamental property of domain walls, but just because of the reason that at some point they dominate the universe, typically what people do when they analyze systems or sourcing of gravitational wave by domain walls, they cut the presence of the domain walls by inserting some annihilation mechanism. Okay, so that effectively transforms domain walls into the first category, into a fast source. And that's why domain walls in general, you will observe spectra indeed of this kind, with an F cube and a peak. But this is not a feature, so you simply need this, otherwise you don't get the observable universe. Okay, so for domain walls, it's true that in general they are transformed into a fast source. On the other hand, cosmic strings, they have, they don't have this problem. They reach a scaling. So they behave like the background. And so there is no need to invent a process to annihilate the cosmic strings. And therefore they go on forever. But other kinds of topological defects can also reach scaling. I mean, if you check out this paper, they have all the details here, and they explain the validity of this particular solution that produces this kind of flat spectra. So they are not only for cosmic strings. Another thing that is important to point out is that the situation can be more complicated in the case of cosmic strings, for example, because you can have the gravitational production from loops. Okay, and this is not what I have considered here. Then one needs to do more refined calculations for the gravitational production by loops. We will see it.
So the plane wave approximation, the sinusoidal, that passes through, like if it is string or monopole. So that's what I was wondering. Because your
the sinus here, this is the green function.
Yeah, because there is an extra source, right? Because of the string or texture. So there should be an extra Green's function like Lippmann-Switzer or like, so that's what I was wondering. Would there be an extra term in the Green's function? So that's
I don't think so. The green function does not depend on the source, right? The green function is determined by this part of the equation.
Oh, okay, homogeneous. Yes.
Yeah, if you use the Wronskian method to solve the equation, then you have the product of combination. So what gives the green function is the product of the combination of the homogeneous solution times the source.
Thank you.
So the sinus here, sinus cosinus will not change. The sinus cosinus here inside will not change, but this solution is not taken, is not adapted. Okay.
Okay, I don't see any further questions, so please go on.
Okay. Okay, so I will now go through a bit what I just sketched quickly yesterday. So the first mechanism that we see that provides an extremely rich phenomenology for the production of gravitational waves is inflation. Okay, and I mean, I don't need to repeat what it is, but the point is that the universe at the end of inflation is characterized by small metric fluctuations of quantum origin that are both scalar and tensor. Okay, scalars, we have detected them. They are of the order of 10 to the minus 5, so very small at the scales at which we have detected them. So large scales, CMB scales, and they provide the density perturbation that have formed all the structures today. On the other hand, the tensor component is yet undetected, which actually is putting very strong bounds on inflationary models. Okay. So what happens with respect to this source? Well, in this case, we consider the production of gravitational waves from the quantum fluctuations of the background and the fact that these quantum fluctuations are amplified by the exponential expansion driven by the inflaton, and therefore we have no source here. We deal with the homogeneous equation, and we find basically the same solution that I showed you in the second lecture, okay, in which one actually needs to, so this I didn't do in the second lecture, but in general one needs to quantize the tensor fluctuation, okay, and one can rewrite with this canonically normalized field the equation in this way. And here you have, as I already said, this time-dependent frequency, and one can split the solution into sub-bubble modes, which will just give a free field in vacuum with zero occupation number, and superable modes, which instead have a very large occupation number. There is also, of course, as I'm sure you know, a way to solve this equation continuously using a Bogoliubov coefficient. Okay, and so in the end, basically, this is the irreducible component of gravitational waves from inflation. Typically the calculation is done in the context of slow roll inflation. Okay, so it is this gravitational wave spectrum is really generated when the universe the universe is in this phase dominated by the vacuum energy of the scalar field, which is almost constant. Okay. And so the final result is a spectrum that is proportional to h squared over m Planck squared, and it has a dependence on the wave number, which is in general tiny. Okay, because this parameter epsilon is the first slow roll parameter, so it is related to the variation of the potential with respect to the field, and this is by definition small in slow roll. Okay, and then one needs to, so this is the spectrum at super horizon modes, so it corresponds to this constant that I already showed you in the beginning, where we have indeed, now we know what is the actual amplitude here. I just called it a constant in the second lecture, but if you specify, of course, that it comes from slow roll inflation, that's what you get. And then you have the transfer function during the radiation matter era when the modes enter the horizon. And indeed, here you see what is the final spectrum. So it is flat for modes that enter the horizon in the radiation era, and it goes like 1 over f squared for modes that enter the horizon, in the radiation era, and 1 over f squared for modes that enter the horizon in the matter era. Okay, so omega is going to be proportional to the primordial spectrum times this transfer function. Okay, so there is a way to rewrite fully the transfer function. These are fits actually, because if you do the calculation, you get all these oscillations, etc. Because of course the solution starts to oscillate once they re-enter the horizon, they become gravitational waves. But in general, this is what is written. Okay, so in terms of frequency today. You convert this k to frequency. This is in general called NT, the tensor spectral index, and then you have this particular form after equality for modes that enter the horizon after equality, and just a constant for modes that enter the horizon before equality. And in general, the amplitude is given in terms of the tensor to scalar ratio that has been, of course, bound now by CMB observations, while PR here is the scalar amplitude that has been measured. And as I said also in the first lecture, in this case, the signal extends in frequency, at least in principle, from very large scales corresponding to the Hubble scale today up to the Hubble scale during inflation. Okay, so up to the upper cutoff that is due to the beginning of inflation, that of course we don't know, the energy scale of inflation. Okay, and so this particular case can also be somehow seen as a continuous sources of gravitational waves as mode re-enter the Hubble horizon. So it's not completely different than what I was saying before, although it is not really a sourcing. I mean, it's just the fact that the modes re-enter the Hubble horizon, but this goes, in agreement with the fact that this spectrum is basically flat. Okay. So now, if you look at this particular plot here that you have already seen, I already showed you, you see that the calculation, the calculation, or at least the calculation performed in the range of scale where we have observations is here at very small scales, small frequencies. Okay, and one can, of course, somehow, in the absence of a better model, one can assume, okay, slow roll goes all the way. Okay, and therefore extend this particular flat, almost flat spectrum up to very high energy scales that here would correspond to the energy scale of inflation. Okay, and in this case, of course, here we have the amplitude, okay, that is bound by observations, and so the energy scale of inflation can be at best 10 to the 16 GeV or smaller, which means that this particular plateau is either at this level, okay, at the level of 10 to the minus 16 in omega, or smaller, okay. So this particular signal is not detectable by future interferometers, neither present nor future interferometers. Of course, one can turn the situation, and instead of saying, we are sure that we have slow roll inflation up to the end, up to reheating, and we cannot observe it, one can say, but wait a second, we can actually use these gravitational wave observatories to probe the inflationary spectrum, the tensor inflationary spectrum, at scales at which the CMB does not constrain it. Okay, so this is sort of another point of view, a positive point of view that says, okay, but what is the reason why this particular spectral index should be flat, or slightly negative for the entire gravitational, for the entire inflationary epoch. Okay, let's suppose that something else can happen. Okay, and so then there are extremely a wide variety of proposals to change the situation, and typically those that are the most interesting from this point of view are those that enhance the spectrum at small scales. And one can obtain it by, instead of considering, as I was here, just the homogeneous solution, by putting a source. Okay, and in general, then, to have an active source of tensor modes, during inflation, one needs to add extra fields, but one can also, on the other hand, enhance this by modifying the inflation potential. Okay, one can also modify the gravitational interaction, or one can add, at the end of inflation, a phase with a stiff equation of state. Okay. So there are proposals, as I was saying also yesterday. Here I give a couple of examples. So the first one is indeed in this category of adding extra fields, and this will lead to an active source. Okay, and the active source, so typically what one does is that one assumes that the inflaton is a pseudo-scalar field, and one adds gauge fields to the game, and this particular interaction in the Lagrangian, which is absolutely allowed. And this particular interaction then breaks the conformal symmetry of the electromagnetic or the gauge field, and therefore leads to gauge particle production. Okay. And one can see the source as being, in this way, as being the presence of a sort of electromagnetic field that, of course, during inflation is not won't be the standard one, but I mean, you can think about it in this category of sources that I gave in the beginning, something of this sort. Okay, and so this is an extremely rich phenomenology. It can provide non-Gaussianity, also in the CMB scales, which actually constrain the scenario. It can provide chiral gravitational waves, because this is in general a chiral coupling. It can provide primordial black holes, but the truth is that the signal is pretty difficult to evaluate, because at some point you will have back reaction of this gravitational back reaction of these gauge fields on the inflationary dynamics. And there is where people are now providing results by doing numerical simulations of the full system of the inflaton in the Friedmann metric coupled to these gauge fields and how the whole system evolves. But here we have just an example of the spectrum from these very old papers. And you see that in general, when you are able to approximate these as subsequent slow-roll phases, you get a positive signal. Okay, so you get an enhancement with respect to the almost flat or slightly negative slow-roll case. Okay, it's an extra production of gravitational waves. Okay, the other example that I wanted to give, which we have already considered, mentioned a couple of times in this lecture series, is the one of second-order scalar perturbation. So I don't need to go through here what is the situations, because we have already described it. So in all generality, one has the production of gravitational waves by a kernel which is given by a source which is given by some complicated kernels that you can find in the literature, and the quadratic is quadratic in the power spectrum of the curvature perturbation. Okay, so it's quadratic in the scalar mode. And of course, now the problem is that this signal, first of all, it requires to be observable an enhancement of this quantity that otherwise is of the order of 10 to the minus 10, right? So we need to have an enhancement of this quantity in order to provide a visible signal. This enhancement can only be obtained, of course, outside this constrained region, so at high frequency, but that's okay because is where we actually need it to be observable by gravitational wave interferometers. But then this means that the signal widely depends on what you assume for this for the shape of the curvature perturbation at small scales, where you have indeed no guidance, no observational guidance. Okay. So what can generate this kind of enhancement is typically some what is called an ultra slow roll phase towards the end of inflation. So one has the slow roll phase, that drives the exponential or quasi-exponential expansion at large scales, and this is what you need to get the CMB observation, right? To get all the observable universe exiting the horizon, and providing this homogeneous initial condition. But then towards the end of inflation, one can add an ultra slow roll phase, and this actually enhances PR simply because I'm sure you know PR is proportional to 1 over epsilon. Okay, so when epsilon is very small, PR becomes very big. Right, and then in this case, the source is a combination of, as I said, the gradients of the Bardeen potentials. And what is also nice to point out in this context is that there is, in general, an associated production of primordial black holes. Because this high curvature perturbation, these are once they re-enter the horizon during the radiation era, they lead to overdensities of order 1, which can collapse and form a black hole. Okay, and this is just an example of a signal that I taken from okay, sorry, somehow the reference went away. These are papers by the Padova group, in which they have first pointed out a very interesting property, and that's why here I gave this example in the LISA band. Okay, here you can appreciate how the signal can be different depending on which assumptions you assume for the curvature perturbation. Okay, this is a delta function and some sort of Gaussian. But what is nice to point out here is the fact that in general, if there is a signal from the second order scalars in the LISA band, this would correspond through this relation to primordial black holes with masses that are in the only range of masses that is still free from constraints. And so one could have that the totality of the dark matter is in the form of primordial black holes, and at the same time that LISA picks up a very relevant gravitational wave background. So this would be, I think it's a very motivated case for LISA, for observation of a stochastic background with LISA. At the same time, it is important here to point out that the predictions of the signal are very uncertain because they can, so in this case, a Gaussianity of the curvature perturbation is assumed, while on the other end, because it is enhanced, this is exactly the case in which the curvature perturbation will be non-Gaussian. So there is a literature that is trying to tackle this problem to get predictions that are more reliable for the signal. Okay, so another possibility of gravitational wave production at or connected to inflation is a resonant particle production at preheating. This is quite an old idea, and the idea is that, of course, you expect during reheating some kind of coupling of the inflaton with either the standard model particles or intermediate or mediator particles, because you want to transfer from the vacuum energy to the thermal dominated phase, to a thermal phase in the universe, okay? And so under some conditions, you can have that there is a resonant production of these particles, okay? And therefore, this leads to an extremely inhomogeneous situation during this phase that is called preheating. And one can have gravitational waves sourced by, gradients in the sky field, that in this very simple setting is assumed a scalar, but one can have also gauge field. One can play with what, the model is actually free because no one really knows what has happened back then. Now, this signal in general peaks, so this is another example, is an example of spectra taken from this old paper, just to give you an idea that people have been performing simulations to find gravitational waves from this particular mechanism since 20 years ago. And in general, this spectrum is peaked at very high frequency, okay, because it is connected to the scale of inflation. It is not due to the re-enter of super horizon modes. It's really something that is localized at the moment of reheating, and that's why typically you see that these are also peaked spectra. Okay, but nowadays I just wanted to point out that there are many proposals for the possibility to detect gravitational waves at high frequency. And therefore, for now, the sensitivities are extremely bad, but maybe with progresses in the future, one will be able to get close to the predictions of preheating of this kind of models for the detection. Okay, and I want to close the chapter, let's say, of examples from inflation, which is, by the way, not complete at all, just by giving an example of a possible detection at pulsar timing arrays. Okay, so in the European pulsar timing array collaboration, we have considered the possibility that the measurement of a stochastic background from pulsar timing arrays comes from inflation. Of course, it's a bit stretched. It's a bit of a long stretch, but why not? Nothing forbids it. And so we have taken an analysis first in which we have considered then some spectrum in which we have left free both the tensor to scalar ratio and NT. So this is completely disconnected from the Slorol hypothesis, okay? And we have just seen, okay, let's see what kind of constraint pulsar timing arrays can put on this particular signal with its transfer function, okay? And this is the result, and you see that the value of R are unrealistically small, of course, because one needs to satisfy CMB constraint at small frequency, and at the same time one needs a huge tilt in the power spectrum to get something visible in the pulsar timing array band. Okay, so that's why NT is so big. So one finds a very small R and a very high NT. So I'm not claiming that this is natural at all, but just that, if one actually completely relaxes the slow roll assumption and infers what are the CMB bound from CMB observation on NT, one is actually not, it is in principle still allowed. Okay, another possibility would be instead to assume that NT is compatible with slow roll, so slightly negative, close to zero and slightly negative, and enhance the spectrum with the stiff equation of state with W larger than 1/3. Unfortunately, the best fit scenario, the best fit value of the power spectrum in EPTA is of the order of 2.7, okay? And this is the typical relation between NT and gamma, which is the parameter, as we saw a couple of lectures ago, the parameters that they actually constrain. But the modulation from a stiff equation of state is something that is comprised between 0 and -2, okay, and therefore, one finds that to be compatible, you need NT that is still, okay, much smaller than if you don't put this term, but is still slightly larger than 0.3, so it's not really fully compatible with slow roll. Okay, so that ends my sort of short review of inflation, and now we go to phase transitions like Gut or Peche-Quinn that lead to topological defects. Okay, so we'll get a bit more detail on topological defects. So, as you all know, this can be formed by symmetry breaking, right? Depending on the property of the ground state, the new ground state. So the typical example in a global U1 is the formation of cosmic strings. And now, really here, what is important to notice is that, there is a huge freedom both in the modeling, but also when one restricts to a model, a huge freedom in what is actually the shape and the characteristic of the gravitational wave spectrum. Okay, so first of all, the properties, basically there are as much defects as there are underlying actions. So one can have strings, domain walls, textures, etc. They can be stable, or one can make them to annihilate if they disturb. One can have different thickness. One can ask what is their energy per unit length or surface. That is what then enters the gravitational production. They can be interacting. They can have additional degrees of freedom. For example, carry currents. What is their dynamics? This is particularly difficult because one needs in general to resort to numerical simulations to find it. But regardless of all this freedom, what one can say is that these are concentrations of high energy density with relativistic velocity, and so in general they are powerful sources of gravitational waves, okay, regardless. On the other hand, they can also be sources of other kind of radiation, typically particles, the particles of the field that underwent the transition, for example, the particles of which they are made, sort of. So a huge question is, what is the dominant decay mechanism? Do they decay more into particles or into gravitational waves? This can also be positive because it means that there can be multi-messenger observational signatures, but depending on which kind of radiation they emit, the network can or cannot reach scaling. Okay, so bottom line is that numerical simulations are absolutely necessary to model the evolution of topological defects, but the problem is that in general, they need a very large dynamical range because in general, you cannot, they would need a very large dynamical range, but in any case, you cannot resolve the small scales that, for example, will lead to the particle production from the scales of the universe, which will lead to modeling the dynamics of the or the dynamics of the network, the large-scale dynamics of the network. And in general, these simulation, which they don't do always, they should contain the gravitational back reaction, so how the network or the gravitational wave production back reacts on either the background or the network itself. Okay, so this leads to the fact that the prediction of the gravitational wave signal from topological defects is inevitably model dependent. Okay, that doesn't mean that one cannot do predictions, okay, but it is important to keep this in mind. Okay, so the case that is the most studied and the most favorable for gravitational wave production are local cosmic strings arising from the breaking of a local Yuan symmetry at some energy scale, okay, eta, which is then related to this parameter g mu that enters all the gravitational wave properties of the strings. And if one assumes, in general, it is assumed that they can be described by the Nambu-Goto action, okay, which means that the inverse of this energy scale is much smaller than the length, so the width of the string is much smaller than their length. Then what the simulations find is that these strings intercommute and form loops, and these loops, they have kinks and cusps that can produce, together with the loops oscillation, gravitational waves, okay, very powerful gravitational wave sources. And it is thanks to this chopping out of loops and emission of gravitational waves that the network reaches a scaling regime. Okay, so that we, as we were saying before, we don't need to get rid of these cosmic strings because they don't perturb the universe. And now there are a lot of questions that arise, what is the gravitational wave power radiated by the loop? Does the loop also emit other kind of radiation? What is the loop distributions? What is the role played by gravitational back reaction? So all these questions, they don't have answer, I think, or at least commonly accepted answers up to now. And that's why different numerical simulations provide different prediction for the gravitational wave signal. And so here you see, for example, the examples in two distinct models, okay? And now here I just want to flash the constraints, future constraints that one can have, for example, with LISA. So assuming this kind of scenario for the signal, and LISA is extremely powerful, could constrain G mu values down to 10 to the minus 17, while now the constraints by Largo Virgo Cagra, the actual constraint on this particular model are of the order of 10 to the minus 8. So you see, you get almost 10 orders of magnitude best constrained with LISA. And also, of course, third generation detectors will provide an improvement in the constraints, and on this model, which is here the continuous curves, one can constrain G mu accounting or not accounting for foregrounds, let's say accounting for foregrounds down to the level of 10 to the minus 15. Okay, which means probing energy scale down to 10 to the 11 or 12 GeV. Okay, so this allows to really look far in the past. far in the past of the universe. So this, even though there are all these uncertainties, it is extremely important to pursue this kind of analysis, because topological defects, they really offer the opportunity to probe energy scales in the universe at which we have absolutely no idea what occurred. Okay, and now I want to just provide, as well as before, an example of possible detection at pulsar timing arrays for local cosmic strings. Okay, and you see here again the two spectra that I showed before, that are actually pretty much the same in the frequency range of pulsar timing arrays for the G mu that could explain the signal. And here you have the constraints on G mu in the two models. Okay, so this is the one that I quoted, and it gives a constraint. So it's not a constraint here. So if what has been observed by pulsar timing arrays corresponds to cosmic strings, is due to cosmic strings, then they would be cosmic strings with a G mu of the order of 8 10 to the minus 11, so a scale of 10 to the 14 GeV. Okay, but turns out that cosmic strings are not the best fit to at least the EPTA, but also the nanograph data, because the spectrum is a bit too shallow. You see here okay. So I want now to go a bit more detail in topological defects, as I said before. In particular, we consider the case of domain walls. Okay, so these are formed when a discrete symmetry is broken and the ground state is disconnected. Okay, and they also form a network that is thought to reach the scaling regime, also by reconnection and radiation emission, but the energy density decays too slowly, as I was saying before, so it actually comes to dominate the universe, and therefore one needs an annihilation mechanism to get rid of these domain walls. And in general, one does it by introducing some explicit breaking of the discrete symmetry after the phase transition that have generated the domain walls. And so one supposes that the potential is slightly tilted, and therefore this vacuum non-degeneracy will actually favor one of the two vacua, and then the domain walls will annihilate at some temperature. That is when the Hubble scale becomes comparable to this delta V. Okay, and now we have that the signal, as I said before, because you need to restrain the production of gravitational waves or the lifetime of this network, the signal is in general peaked. Okay, and it depends, so it has a peak frequency that corresponds to h at annihilation, and some amplitude that corresponds to the ratio between the energy density of the domain wall and the energy density in the radiation-dominated universe at this annihilation temperature, while the spectrum really depends on the detail and is generally taken from numerical simulations. Okay, and so one can, in this parameter space of the annihilation temperatures over this amplitude of the gravitational wave signal, one can study the reach of different detectors to constrain this particular scenario of production of domain walls. And you see here the potential reach of third generation interferometer, LISA, and the SKA. Okay. And now, so I only have 5 minutes left. I want to go to phase transition, so I will try to be fast. So these, of course, we know that there are two phase transitions that must have occurred in the early universe because they are predicted by the standard model of particle physics, and these are the electroweak and the QCD phase transitions. And according to the standard model, these are both crossover. Okay. However, sizable gravitational wave generation absolutely requires a first-order phase transition. Okay, so not a crossover or a second order in which the potential changes with the temperature like this, just developing the true minimum, but a situation in which a potential barrier is formed between at critical temperature and then persists between the false and the true vacuum. Okay, if we have this potential barrier, this means that in real space we have the nucleation of true vacuum bubbles, and this is what generates the generation of the gravitational waves is connected to this bubble nucleation. Okay, so this is the phase diagram in the context of the standard model, both for the electroweak phase transition and the QCD phase transition, and you see that they are both predicted to be crossovers for the X mass for the mass of the X, and here at zero baryochemical potential. However, they can both become first order. So in the case of the electroweak phase transition, one needs to extend the electroweak sector, which is done in the context of beyond standard model theories. In the context of the QCD phase transition, in general, this might be related to the presence of a lepton asymmetry in the universe that can change the trajectory here, the value of the trajectory. Okay, and there are also many other examples of possible first-order phase transitions in the early universe, okay, in the context of effective approaches, conformal models, etc., the Apache Queen. So, it is also worth to study this particular source because it provides the opportunity to probe once again high energy physics scenarios beyond the standard model. Okay, speeding up a bit, I already told you that the gravitational wave production is linked to the presence of these vacuum bubbles, and it is in particular, occurs in particular when the bubble collides towards the end of the phase transition, either by the scalar field gradients, by bulk fluid motion due to the presence of the bubbles, or by electromagnetic fields. And in general, here as well, there is maybe a bit less variety in the spectral shape of the gravitational wave spectrum than in the case of topological defects, but there is a big dependence on a bunch of parameters that are, for example, the temperature at which the phase transition is taking place, but also the velocity of the bubble walls, the fractional kinetic energy that is in the anisotropic stresses, the inverse duration of the phase transition, how much vacuum energy is available, so how strong the phase transition is. Okay, and here as well, though most of these parameters are at least in principle known given a phase transition model, numerical simulations are absolutely necessary to infer the gravitational wave signal. And here, once again, to connect to what I was saying before, the signals are picked, okay, because these are fast processes, and you see how they vary depending when one actually varies these parameters, okay, so what is the dependence on the parameters. So I will just take maybe a couple of minutes more and go very fast here. So in the context of these picked signals, one can make a correspondence, as I already said, between the frequency of detection of the particular gravitational wave detector and the energy scale. at which the phase transition is occurring, and in the context of Earth, the frequency span of Earth-based detectors, one is sensitive to the energy scale of the patchy phase transition. For pulsar timing arrays, one can probe the QCD energy scale, and for LISA, one can probe the electric energy scale. So we see that we are well equipped to probe interesting scenarios. And here I'm just flashing two examples of parameter reconstruction done at LISA. So where you see this is the sensitivity of the instrument. These are the foregrounds I already told you about, and this is the signal from first order electric phase transition, and this is how you can actually reconstruct the parameters I was telling you before, for example, the energy scale of the phase transition and its inverse duration with, in some cases, very strong degeneracies. Okay, and this is an example of a possible detection, once again, at pulsar timing arrays. So if we assume then that the pulsar timing array signal is not due to supermassive black hole binaries, but to, for example, the presence of magnetohydrodynamic turbulence due to the QCD phase transition, okay, at the QCD scale, then this is the particular spectrum that one produces. It has a break at a scale that corresponds to the horizon at the QCD phase transition. And here is the reconstruction in the parameter of the signal. For example, here you recognize again the energy scale of the phase transition, which is now, you know, around the MeV. The parameter reconstruction, you know, if we assume that the signal is due to this particular mechanism. And I mean, this, you know, there is a good fit actually from this prediction of the spectrum. But the conditions are that one needs a huge amount of energy, of relative energy, to be able to explain the PTA observation with this kind of signal. Okay, so I reach the end. So this is a summary, let's say, of this last part of the lectures, which I think is in some sense the most important, because it really opens up on the research that is ongoing research nowadays. Okay, so we have seen that gravitational wave background might reveal a powerful tool to probe the early universe and consequently high energy physics. Unfortunately, to be able to distinguish all this huge variety of proposals and to be able to infer the characteristic of the source, the spectral shape must be predicted with extremely good accuracy. And this is not often the case. But I have also showed you that one has some guidance, general considerations about the characteristic of the spectral shape are possible in some cases, you know, to pin down at least the class of gravitational wave source. For example, if you observe F cube and maybe some peak, you know, okay, at least this is a fast source. If you observe a flat signal, possibly many interferometers, then, okay, you say, good, then this is some sort of topological defect. Right, and then we have seen examples. So during inflation, one needs, of course, to go beyond the classical slow roll scenario to have something visible. But this is observationally compelling, okay, because these gravitational wave signals offer the possibility to probe inflation at scales complementary to CMB scales. Okay, for topological defects, they have this amazing potential to probe high energy theories, but one needs to account for the fact that the gravitational wave signal is pretty much model dependent. We have seen the possibility to probe the electric phase transition, which is also extremely interesting with LISA. Because this is the limit of tested towards untested physics, and so LISA can in principle provide constraints on models. And also the same can arise for the QCD phase transition at pulsar using pulsar timing arrays. Okay. So this signal might seem speculative, but their potential to probe fundamental physics is absolutely great. Okay, thank you very much. I'll take questions now.
Thank you very much, Chiara, for this wonderful summary. Other questions? Yeah, I'll start one. So this, if LISA does not observe any stochastic gravitational waves, this would imply a serious constraints on some of the beyond standard models?
So it will imply for sure some constraints. I would say the simplest scenario is where you extend the standard model with light scalars. There you can have strong signals, and what won't be possible to do, is to somehow really connect. If there is a detection, it is impossible to connect or infer from what theory the signal is due. But the other way around, calculating signals within models and calculating a gravitational wave signal and inferring constraint is always possible. And so, yes, it would provide now, I don't know whether I would classify these as strong constraints. It depends really on the model, but it will certainly provide some constraints, yes.
I see. In the next few years, the pulsar timing array constraints could do the same thing or similar thing even before LISA?
Yes, so exactly. So the pulsar timing array, you see here, we have already played the game to say, okay, what about if we want to fit the pulsar timing array signal with gravitational waves, arising. In this case was magnetohydrodynamic turbulence after a phase transition. So of course, in the future, what we will have is that this kind of data set will become more and more precise, and we will have more frequencies also that will add as we add pulsars to be observed and as the time span of observation increase. So it will be easier and easier to constrain, because here from this plot you can observe the huge degeneracy that there is in predictions with respect to the data. So if the data get better, you can actually have much more opportunity to constrain much better the spectral shape. Okay, and then this is point one. The other thing is that as the data get better, and one hopes to be able to constrain the anisotropy on the sky of this signal that has been observed by pulsar timing arrays, because everything that comes from the early universe is, of course, fully isotropic. But if it comes from supermassive black hole binaries, one would see the signal as being stronger in correspondence to the direction where the strongest sources are. And so if one observes anisotropies, then it is a strong hint that everything that comes from the early universe is excluded. So this is also, somehow what one needs to do or to look for in the future as pulsar timing arrays data will become better.
Thank you. I don't see any further questions. Okay, Prasad.
So you mentioned that the QCD phase transition in the early universe can also show up in the LIGO and the ground-based detectors. So how good those constraints will be by the non-observation of QCD phase transition?
No, so not the QCD one. So the QCD one is at frequency of pulsar timing arrays. Okay, so in the context of Earth-based detector is the Petrie-Quinn phase transition that can be constrained. Okay, because the typical scale here of this phase transition has been constrained to be, around 10 to the 7 to 10 to the 11 GeV. And this really corresponds to the frequency range of Earth-based detectors. Okay, and here you see, so in this parameter space that is, here there is the energy scale of the phase transition, and here there is the inverse duration. You see what kind of constraints can be put, what kind of constraints LIGO Virgo Calgra already put, and what kind of constraint Einstein Telescope and Cosmic Explorer will be able to put on this parameter space. Now here, of course, this is not, here we are somehow specifying that the Pechequin phase transitions occurs in models in which it is first order and it leads to the production of vacuum bubbles. Okay, these are not all the models within which the Pechequin phase transition can be accommodated, but there is a class of models in which this is possible.
Okay, thank you.
So yeah, so it will constrain those class of models. Yeah.
Okay, let's thank Chiara for this great overview of different gravitational wave generation mechanisms in the early universe and using the possibility of stochastic gravitational wave observations to constrain them. Thank you very much, Chiara.
Thank you very much for the invitation. Bye-bye, everyone.
Thank you. Bye-bye.